In first year chem, I usually tell kids that if you like mole calculations and stoichiometry, AP is the class for you. Stoichiometry is something that you're going to use all year long. So it's a skill that must be mastered, and it should be something that comes pretty naturally for you. You can set up these proportions and apply it to a balanced equation pretty easily. We shouldn't have to sit and think for 20 minutes on how to start a stoichiometry problem. If you find that this is not coming back to you quickly, or for some reason you say, I never understood stoichiometry to begin with, it's definitely time to stop in for some extra help one-on-one. This should be all review. So we should be able to go through it pretty quick. And with a couple practice problems, it does come back to you. It's a method. And hopefully that method is something that's familiar to you. We're looking at ratios in balanced equations, comparing amounts of reactants and products. And we can look at that ratio in a balanced equation a couple different ways. So here down in this box, we've got a combustion of methane. It's a fun reaction. We'll do that a couple times. If I look at the ratio in a balanced equation, most people, when they're balancing the equation, think of it as a ratio of atoms or molecules. And we would probably read that as 1 molecule of methane plus 2 molecules of oxygen produce 1 molecule of carbon dioxide and 2 molecules of water. And there's nothing wrong with that until you want to start going into the lab. In the lab, I can't measure atoms and molecules. So I know that's the ratio that I need to run this reaction, but I can't physically do that. I can't pull out 1 molecule of methane. So now on a larger scale, we think about this as a mole ratio. It's still a consistent ratio of particles in a balanced equation, but it just is a way of measuring amounts that are reasonable in the lab. 6.022 times 10 to the 23rd molecules of methane would have a molar mass of about 16 grams. Can I measure 16 grams in the lab? Absolutely, that's reasonable. I could not go find 2 molecules of oxygen, but I could measure 2 moles of oxygen molecules. It'd be about 12 times 10 to the 23rd molecules, or approximately 64 grams. Each mole of oxygen, O2 diatomic, is about 32 grams. I got 2 moles, so about 64 grams, giving me a total amount of 80 grams on the reactant side. I can apply that same concept to the product side. We'll use this ratio as a mole ratio, so it's just a larger quantity, but it's a consistent ratio of 1 to 2. For every 1 molecule of carbon dioxide, I get 2 molecules of water. This is just a few more than 1 and 2. And then if I use moles, I can look up molar masses. And these should be numbers that are reasonable to measure in the lab. Could I measure 44 grams? Of course. I can measure 44 grams of carbon dioxide. 2 moles of water. Each mole is about 18 grams. Can I go measure 36 grams of water? You bet. Giving me a total of 80 grams product. So that law of conservation of mass still holds true. Whether I look at it as, atoms of carbon, every atom must be accounted for on both sides, or now I can kind of think about it as grams too. The total mass of the reactants needs to be the same as the total mass of the products. So we're most concerned with this guy, the mole in the middle there. Moles and molar masses. So let's see if we can refresh our memory on some basic stoichiometry. Actually, I think there's one hiding down here. There it is. Iron oxide. We can form iron oxide from a simple reaction of iron and oxygen. Unfortunately, that happens in nature to your nice shiny cars. We want to know how many moles of iron oxide will be produced if 1.63 moles of oxygen react with iron. Okay, so we usually have one number to start with. And I start with that 1.63 moles of oxygen in this case. You got to start with the unit and the quantity. And again, sometimes people want to just quick plug this in their calculator. I want a quick fix. But you got to show work on the AP test. You got to set these up. So here's what we're looking for. We're looking for ratios and proportions. So I have my oxygen. But I don't want oxygen in the end, so let's cancel moles of oxygen. We want to know how many moles of iron oxide can be formed. What you want goes on the top. That's a messy M. Moles of iron oxide. Now I just plug in the ratio from the balanced equation. That ratio represents moles. It's a 2 to 3 ratio. And again, I get kind of antsy here that I can cancel like terms. I like that. And then we just plug this in our calculator. I multiply by 2, divide by 3. The first number has 3 sig figs, so let's leave 3. Let's say about 1.09 moles of iron oxide. And I get it. Some people can probably do that in their head. These simple mole calculations. I mean, sometimes it could be just, oh, I need to multiply by 2 or divide by 2. You can do that in your head. You can do it in your calculator. But on the AP test, they will want you to show all their work. So this is what we're looking for. We're looking for these proportions. All right, let's go a step further. Let's make these more fun. Those are too easy. We've got the balanced equations for these, so that's kind of nice. You don't have to worry about balancing the equation yourself or getting it wrong because somehow I maybe didn't write the formulas correctly or something like that. I want to know how many grams of lead nitrate is needed. I'm looking at a reactant to produce 1.85 moles of lead 2 sulfide in the reaction between the lead nitrate and sodium sulfide. This is nice. I got the balanced equation, and I want to produce a certain amount of product. So we're going to start there. We want 1.85 moles of that lead 2 sulfide. That's what I want to produce. So I'm working backwards. Then if I go in the lab, how many grams of that lead nitrate should I start with? This is nice because it's realistic. If I'm going in the lab, I'm probably measuring my reactants in grams. It might be acceptable to only measure a certain amount of product in moles because then maybe I want to compare that to the amount of sodium nitrate or something like that. And I could compare them as a mole ratio. Okay, so I can use the ratio from the balanced equation like that to figure out how many moles of lead nitrate. So let's set this up. I don't want to know moles of lead sulfate. I already got that. Let's go to moles of the lead nitrate. That's an easy switch. And in fact, it's a 1-to-1 ratio. 1-to-1. And now, again, I'm going to cancel these because I like it. Now, could you take a shortcut here? If you recognized, hey, it's just a 1-to-1 ratio in the balanced equation. So if I need 1.85 moles of the lead sulfide, I need to start with 1.85 moles of the lead nitrate. Absolutely. You could take that as a shortcut, and you could start with this with 1.85 moles of lead nitrate. But I wanted to set it all up. If this weren't a 1-to-1 ratio, I would have to put that in there if it was 1-to-2 or 2-to-3 or something like that. I sometimes still like to leave this part in because I am kind of a freak about my units setting up and canceling. So I like this. It was a 1-to-1 ratio. I switched out of the product and I got over to the lead nitrate using the ratio from the balanced equation, which is a mole ratio. Now I get it. The question asks how many grams of lead nitrate would be needed. So that's where I'll go next. Right now my unit is moles lead nitrate. I don't want that. So we'll cancel moles of the lead nitrate. We want this in grams of lead nitrate. What you want goes on top. All right, so now this is like any other mole calculation. The periodic table tells me the mass of 1 mole. I just have to add it up. And this would be something that you can do in your calculator. You don't need to show work for molar masses. Just plug that in. I'm going to take 1 lead plus 2 times the mass of nitrogen and 6 times the mass of oxygen. Little over 331.22. And this makes me feel good to cancel out moles of lead nitrate. All right. right. So the idea, again, is that the ratio in the balanced equation can be used to convert between moles. If you don't want your final answer in moles, you'll need to convert it back to grams in this case. Now I can just plug it all in my calculator. This should be an easy one. 1.85. I don't have to do anything with the ones. Times 331.22. The original number has 3 sig figs, so we'll just leave this as 3 sig figs. And we'll say 1, 2, 3, 613. That's good enough. 613 grams of lead nitrate. Done. There she is, stoichiometry at its finest. It makes sense. It's got to make sense. Use the ratio from the balanced equation to switch between moles of different substances. Then just check the problem and see what you want your final answer in. Do you want it in moles? If not, it's probably going to be grams. Then we'll just tack on that last switch. Calcium chlorate decomposes into calcium chloride and oxygen. I have 14 grams of calcium chlorate. Exactly 14 grams of calcium chlorate. I want to know how many moles of oxygen can be produced. Excellent. So I want to make a switch from this reactant over to this product. But I can't make the switch in grams. It's a 1:3 ratio, but it has nothing to do with grams. Those compounds will have very different molar masses. The 1:3 ratio represents a ratio of particles, or moles. So if you start with a number in grams, before you can switch on the periodic table, I need to add up this molar mass and get it out of grams into moles. So we're going to cancel grams of the calcium chlorate. I need moles of calcium chlorate. 1 mole should have the mass on the periodic table. You add it up. You don't need to show work. Let's go 206.98. That was 1 calcium, 2 chlorine, and 6 times the mass of oxygen. All right. I like this. If I were to plug it in my calculator right now, I would have moles of calcium chlorate. But I can just tack on this next switch and we'll plug it all in at once. I'm at moles. I can use the ratio from the balanced equation to compare moles of calcium chlorate and moles of oxygen. Let's cancel moles of the calcium chlorate. I don't want that. We can use the ratio to get over to moles of oxygen. It's a 3-to-1. And if I look back at the problem, that's what I need. I want to know how many moles of oxygen will be produced. That's the only unit that I have left. I haven't crossed off. We can plug this all in our calculator now. Get a little more room. So we're going to, let's see, take 14. We're going to divide by 206.98. Multiply by 3. The original number is 14, which is 2 sig figs. So I'm going to leave this with 2. Looks kind of goofy. Let's say 0.20 moles of O2 oxygen. I like that. If I'm given moles, I can switch right away using the ratio in the balanced equation. If I'm given grams, I need to put it in moles first. Then I can switch between different substances. Here's one more kind of fun option, dealing with gases. Now, with gases in stoichiometry, sometimes you can use that 22.4 liters as the volume of 1 mole of any gas at standard temperature and pressure. But you need to know that it's at standard temperature and pressure, which we are not told in this problem. Instead, we're given density. The density of hydrogen is given as a ratio between grams and volume. Well, maybe we can somehow use that in the end. I want to know what volume of hydrogen I could produce when 2.5 grams of zinc react with an excess of hydrochloric acid, meaning there's plenty of hydrochloric acid, but the zinc must be my limiting reactant. The zinc determines how much product is formed. Okay, so we're given an amount of zinc. We want to know about the hydrogen. Okay, well, I can't compare these things in grams. So I know that I'm going to want to start with this 2.5 grams of zinc and get it out of grams zinc and into moles. Moles of zinc. 1 mole has the mass on the periodic table, 65.39 grams. Goodbye. Right now I'm sitting at moles of zinc. Now I can make the switch between moles of zinc and moles of hydrogen. And again, it's a 1-to-1 ratio. So if you wanted, you could plug this in your calculator and just kind of start fresh. But I'm going to keep all these things going. Let's cancel moles of zinc and switch it to moles of hydrogen. I get it. It's a 1-to-1 ratio. It's not going to change my final answer, but I like it because I'm a freak about my units being in the right spot at the right time, and I want them to cancel and all work out in the end. So I keep it in there. It wasn't that hard. So right now I'm at moles of hydrogen. If I knew this was at standard temperature and pressure, I could use that 22.4 liters as the volume of 1 mole. But I don't know that it's at standard temperature and pressure. The only thing that kind of hints at volume is that density, a ratio of grams to liters. Well, let's switch this to grams of hydrogen. Let's tack on another proportion, get this out of moles, and let's switch it to grams. That's not so bad. 1 mole of hydrogen should have the mass on the periodic table. It is diatomic. So we need to multiply the mass by 2. And then moles would cancel, and I'd be sitting at grams. Now I think I could put that density in. Let's tack on 1 more. Cancel grams, put it in liters. When I say the density is 0.0899 grams per liter, that's like saying 0.0899 is the mass of 1 liter. Well, look at that. We can cancel grams. The only unit that's left is volume in liters. And again, if I would have known this was standard temperature and pressure, I could have gone straight from moles of hydrogen to volume, because I could have used that 22.4 as the molar volume of hydrogen, the volume in liters of 1 mole, but I wasn't sure. So I used the density. It wasn't so bad. Now I plug all this in our calculator. The original number only has 2 sig figs, so let's just leave 2. 0.86 liters of hydrogen gas. Okay, so hopefully some of this rings a bell. The general method of using the ratio from the balanced equation as a mole ratio. I can't use that ratio unless I'm in moles. So if I'm not in moles, I got to switch it to moles. Then I need to check what the problem is asking for. Do I want my final answer in moles? If yes, I'm done. If not, then I might need to switch it back to grams, or in this case, even grams and then liters. If this stoichiometry does not ring a bell as something that you can feel confident doing, then you need to stop by and get some help. This should be kind of like your bread and butter. We can do this forward, backwards, upside down in our sleep. Stoichiometry will be like the meat and potatoes of this course. So let me know if this is not going smooth for you.